Hi guys, today we're going to learn about Euler's method. We have that a differential equation in x and y is an equation that involves x, y, and the derivatives of y, meaning dy dx. Solving a differential equation analytically can be very difficult or maybe even impossible. However, there are two other approaches that can help doing this. The first one is a slope field. That one is the graphical approach that can be used to learn a lot about the solution of the differential equation, and we learned that yesterday. The other one is what we are going to do today. The name is the Euler's method, and this is a numerical approach that can be used to approximate the particular solution of the differential equation. So how it goes? Suppose that you have a differential equation involving x, y, and the derivative of dy dx. You know that Euler's method is based on the tangent line approximation, so we're going to use the point slope formula. So here you have that it's y times x naught plus delta x. It's going to be approximately y evaluated at x naught plus the derivative of y evaluated at x naught times delta x. This gives you a way to approximate y near the x coordinate x naught, where the value of y of x naught is known. Okay, so this notation might look a little bit intimidating, but don't worry, it's going to be pretty easy once we work this example. Okay, so on this example, what you have is the differential equation dy dx is equal to x divided by y. Okay, so we have that y equals f of x is going to be the particular solution to the given differential equation with the initial condition f of 4 is equal to 1. What we're going to do here is we're going to use Euler's method starting at, in this situation, we're going to start at the point 4, 1, okay? With two steps of equal size. Please note that we're going to do 2 and they are going to be equal size to approximate f of 5. We're going to show all the work that leads to your answer. So what's the deal here? The first thing that I highly recommend you to do is I would do a table. Okay, so this table is going to help you to keep everything organized and very tidy. Okay, so it really helps. Okay, so with that being said, you have that x is going to be here, y is going to be here, and dy dx is going to be over here. Okay, so I think I made the table huge, so let me erase it a little bit. Okay, so you have that. You have a first x and a y, okay, which it comes from the initial condition. You can compute dy dx based on this point 4, 1. Okay, so you know that at 4, 1, your dy dx, or the slope, is going to be 4 over 1, which is going to give you 4. So we have this. Okay, so from this you can technically write your point slope formula as y minus 1 is equal to 4 times x minus 4, simplifying this as y is equal to 4 times x minus 4, okay, plus 1. Okay, so at this point you're going to tell me, okay, now what? Okay, so you have this. We want f of 5, meaning I want this part. Okay, and they tell you to do 2 steps. I already performed my first step, so what's going to be the second step here? If they are equal size, this must be 4.5, because you know that 0.5 is 4.5 is the same distance from 4 than to 5. Okay, so that's why we have 4.5, because they are equal size. Okay, so now you are going to plug when your x is equal to 4.5. You know that the y is going to be equal to what? You are going to plug it into your point slope formula. Okay, so and it's not plus, it's minus 4. Okay, plus 1. So this one is technically the delta x, the change of x, which is 0.5. Okay, so from here you can see that that value will give you, that is going to be 1.5. Okay, no, not 1.5, excuse me, that's going to be 3. Okay, because you have 0.5 times 2, that's 3. Okay, so you have that this is 3. Then what do you have here? You know that at the point 4.5, 3, your derivative dy dx is going to be equal to technically 4.5 divided by 3, which you know that that one we can simplify it as 1.5. Okay, so you have the 1.5 over here. Okay, at this point you can create your new point slope form equation, which is going to be y is going to be equal to 1.5 times x minus 4.5, and then you have plus 3, okay? So when you have that x is equal to 5, how can we find f of 5? Well, you're going to plug 5 here in the new point slope formula. So you have that y is going to be equal to 1.5 times 5 minus 4.5 plus 3, and this one is going to be the beautiful number of 3.75. So 3.75 is the number that we wanted, and we are done. Okay? Thus, here you know that f of 5 is going to be approximately 3.5 according to Euler's method. Okay? So how can we graph this? Okay, so if we want to graph this equation, what you're going to see is my initial point is going to be the point 4, which is here, 1. Okay, so this is your beginning. Okay, the second point that you have here, it was the point 4.5, 3. So 4.5 is around here, and we have that 3 is here. So that's your second point. And the third point that we have is going to be 5 and 3.5. So you have something along the lines of this. If you are connecting the dots, this is your approximation, your Euler's approximation. Okay? Now, what we're going to do for part B is we want to find the particular solution y equals f of x to the differential equation dy dx is equal to x over y with the same initial condition. So as you can see that we have pretty much the same. The only thing that we need to do here is we need to use the solution to find the value of f of 5. Okay? So pretty much here we are going to do separation of variables. Okay? So you have that dy dx is equal to x over y. You know that that's going to be y dy is going to be x equal to x dx. This part we can integrate. If you integrate that, we have that it's going to be y squared divided by 2 is equal to x squared divided by 2 plus c. Multiplying everything times 2, you know that this is going to be equal to y squared equals x squared plus c. Okay, this one I'm going to call that as my general solution. Okay, if we call that as your general solution, I'm going to use the point 4, 1 to find my particular solution. With that being said, I plug these points here, and you have that 1 is going to be equal to 16 plus c, so c is going to be equal to negative 15. Okay, therefore what you have is that your particular solution is going to be y squared is equal to x squared minus 15, and that's going to be your particular solution. Okay, now here I want to find f of 5, so this particular solution needs to be cleaned up. Okay, so you are going to have a situation like this. Okay, so for this problem, what we're going to do is we're going to select the plus, okay, because we're working on quadrant 1 on the graph. Therefore, you know that this is going to be equal to 25, well, 5 squared minus 15, 25 minus 15, that's going to be root 10. Okay, so you know that root 10 is roughly the value of 3.162. So as you can see, comparing this result with the Euler's result, it's close, but it's not that close. Okay, so visually speaking, what do you have? Well, let me draw what we have. We have exactly the same initial condition, but here my endpoint f of 5, okay, which is f of 5 here, you know that it's going to be kind of here. So this is the actual one. Okay, so let's do colors here so you see it. So the pink one is the actual, okay, and here the yellow one is going to be the approximation via Euler's method. So you can see that there's some difference there. Okay, there's an error. Okay, and the further we go, the more we are away from the pink part. Okay, meaning you have an error. Okay, and it's getting further. Okay, so talking about that, let's answer the question for part C. The error in using Euler's method is the difference between the approximated value and the exact value. Okay, so what you have is pretty much the absolute value of the error is going to be equal to, well, your actual minus the approximation, or vice versa, but the absolute value will take care of that. And you have that is going to be minus 3.75. So when you plug that in the calculator, you have that it's 0.588. Okay, so that's the error that we are seeing there in the graph. Okay, with that being said, how could we produce a smaller error using Euler's method? Okay, so you know that we could, okay, we could produce a smaller error, okay, by having more steps, For this problem, what we have is that given the differential equation dy dx is equal to x plus y, let y be equal to f of x be the particular solution to the given differential equation with initial condition f of 4 is equal to -1. We need to use Euler's method starting at x equals 4 with two steps of equal size to approximate f of 4.2, and you need to show all the work that leads to your answer. So what are we going to do here? Like the previous example, what we're going to do is I would recommend you to start with the table so you know what you have, what you're looking for, and basically all the pieces of the puzzle. Okay, so this is the table that I would create. As you know, I would put x here, y here, and here the value of the derivative. Okay, so you start with your initial condition 4, -1, so you start with this one. Okay, over here they told you to have two steps of equal size to approximate 4.2. So over here your end goal is going to be 4.2. Okay, so if we want, this is the first step. Okay, the second step would be 4.1. Okay, in addition to that, now that I have the point 4, -1, I would like to find dy dx. You know that dy dx is going to be equal to 4 plus -1 because we are basing our derivative on this expression. So you know that this is going to be 3. So I would put the 3 here. At this point, I have all the pieces to build my point-slope equation. My point-slope equation for this situation, it would be y is equal to 3 times x minus 4, and then you would have -1. You know that that would be +1 here, but I move it to the other side because I know that I want this expression cleaned up for y. Okay, so here, to find the y here, I'm going to plug the 4.1 in this equation. So I know that when my x is equal to 4.1, I know that my y is going to be equal to 3 times 4.1 minus 4 minus 1. Okay, and we know that that y will give you the beautiful value of -0.7. So you record this here. Okay, so at that point we know that our derivative, okay, so at the point, what was this point? This point was 4.1, -0.7. We have that our derivative, it would be 4.1 plus -0.7, so you know that that's going to be 3.4. Okay, so that's what we have here. Okay, so over here now I have that I have my new slope and another point. So here what you have is that when x is equal to 4.2, okay, you know that the y is going to be equal to your new y, and this y, it would be 3.4 times it would be x minus 4.1 minus 0.7. So I know that this is going to be equal to 3.4, and you can plug the 4.2 here, minus 4.1 minus 0.7. So over here you have that y would be equal to -0.36, and that's the number that we were looking for. Okay, so therefore we can conclude, thus we know that f of 4.2 is going to be, with Euler's method, -0.36, and that's pretty much it for this problem. Well, I hope that you find this video helpful. Bye!